Yeah, good morning, friends in Europe, and good afternoon for friends in China. Thank you for the invitation. Glad to attend this, the first Energy Information Academic Conference Asia meeting. And I come from NARI Technology Co. Limited. So this NARI is the largest manufacturer and also the research and the development institute in China for the second device of the power system. So today I will introduce the cybersecurity for the power system. Cool. Okay, my slides actually there are 5 parts. First, I will introduce what is the cyber-physical power system, because we see the future power system will be the cyber-physical merge the power system. So we call it cyber-physical power system. And the second, I will briefly introduce what's the cyber attack in the power system. And the third part, I will just give one slide to introduce the research framework for the cyber attack in the power system. And then, because this is a full picture of the research, I just use the cyber attack risk assessment and the collaborative defense against cyber attack as 2 examples to introduce part of the components of this research framework. So first is the cyber physical power system. So here is the traditional power system. We can see it's very simple or very clean. So you see on the left side, it's the generation side, and the right side is the consumer side. Then between that, it's the transmission and the distribution. So you can see the flow is actually from the generation side to the consumer side. And also the operation purpose of this system is to keep the balance of the load and the generation. And for this simple system, we already use some IT technologies such as the SCADA and the EMS. So here, the next slide, we call it the new power system, or we also see the trend of the power system. So we see it became much more complicated. The left side, we see some new types of generation like the solar, the wind, and especially the right side, the consumer side. We see a lot of distributed energy resources like the solar, wind, energy storage, and also even the electrical vehicles. So for this kind of system, due to the resources in the consumer side, we see the flow, the power flow is no longer in one direction, it's a bi-direction right now. So for this system, our purpose is how to optimize this all the energy resources, and also how to keep the system flexible, resilient, and connected. So in that case, we need a much more complicated IT system to support this goal. So that's the reason. So in the future power system, we will see more and more sensors and decision-making units, and we will also see very complicated communication networks, and also the scale is very large. And also we see the needs to import the external information like the weather forecast information, the traffic information, and some other information to help this complicated power system stable and secure. And due to this change, we see that the interaction between the cyber and the physical side become more and more complicated. So here we can see that the left side, it's our old system. It's mainly physical, and it's a simple configuration, and it's the traditional. But for the CPPS, so it becomes a multidimensional and heterogeneous and complex. So here, I just list some of the cyber attacks happened in the power system. Some of the most famous one, also the first one that caused the power system outage, is the one in the 2015 in Ukraine. So this one is the first cyber attack caused the power outage in the world. Yeah, we have heard about the attack in the Iran nuclear power plant, but that's not that one did not cause the power system issue. It's just cause the damage or the problem of the nuclear power plant, and it's the first attack that actually successfully attacks the industrial control system. It's not the power system issue. Okay, so the next section, it's a cyber attack in the power system. So first, what is the cybersecurity? So based on the report from the National Institute of Standard and Technology in America, the cybersecurity actually includes the three requirements. First is the confidentiality, and the second, the integrity, and the third is availability. So the confidentiality is to try to ensure only the authorized entities get access to the sensitive information. And the integrity means to ensure any unauthorized modification to data detected. And for the availability, it means to ensure the critical system and information are available when needed. So this one we always call it the CIA. So it's just the first character. We call it CIA. So this is cybersecurity requirements. Then what is the cyber attack? So in the cyber physical power system, so we can define the cyber attacks as those which are conducted on power system or power resources for the purpose of destroying or rebuilding functions of CPPS by tracking the behavior of communication system and the control system in an unpermitted situation, and also exploiting security loopholes and the defects of communication network. So for the cyber attack, we can classify them in different ways. So one is based on the network used. So we can, there are three types. One is the WAN, another one is LAN, and the third one is HAN. So the WAN is mainly used in the generation and the transmission side, and the LAN mainly used in the substation and distribution level, and HAN is mainly used in the consumer level. So they have different attack targets. And also we can also classify the attacks based on the CIA. So here is the first is confidentiality. So this kind of target mainly include like the brute force password cracking, utilization of malware, the virus internal and the internal employee. The integrity can be the false data injection attack, replay attack, or man-in-the-middle attack. Also for the availability, so it's quite common, the DDoS, and also some attack modifying the topology of the communication network. Then we normally know that the power system can be separated into different parts, like the generation, transmission, distribution, and the consumption. So for each part, there are some the weak points or the some of the components that can be the target, main target for the cyber attack. For the generation side, like the local control, the wide area control. For the transmission side, the SCADA system, EMS system, the relay protection devices, and in the distribution side, it can be the advanced meter infrastructure system, the distribution automation, or the distributed energy resources. And in the consumer side, it can be like the real-time electricity price or the electric vehicles. So here I just listed some of them, not all of them, because there are too many components in these different sections. All of them have the potentiality to be the target for the cyber attack, but here just list some of some of them. So here just to give a little bit detail possibility or detailed information on the different the cyber attacks for the different sections of the power system. For the local control, it's we know the generator automatic excitation device and the speed regulation device. So they communicate with the control centers through the Ethernet and Modbus protocols. But this local control, they always connect the data from the local area, and the attack range is small. So the main defense is to prevent the malicious software intruding into the substation LAN and attackers who intrude into the local communication networks and tamper with the digital control logic or settings. And the wide area control, the typical one is the automatic generation control, the AGC. So it needs to use the information from a wide range. So therefore, there's a great risk of AGC control being attacked. So the command text can be the modifying the control loop parameters, the tampering with measurement and control data. And the SCADA and the EMS. So these are typical monitoring, analysis, and the control devices in the transmission level. So attack on the SCADA system may include the illegal operation on the data exchange in the network, such as the intercepting and tampering with the data transmitted by the SCADA system to the control center through fiber optical inverse dropping technology. And on the EMS system include the illegal modification of the state estimation data, the load forecasting data, operators commands, control signal. The WARMS, the wide area measurement system, is a new measurement system. So it can provide the synchronous acquisition and the time-stamped voltage and the current values for the power system protection, control, and the monitoring. And because this needed the synchronize, so its weak point is the time. So some of the attacks can be the synchronization attack. It's a time-based attack, and also some other like the DOS attack and the data injection attack. For the distribution side, there are a couple ways to do that. The first is the AMI. So AMI is to connect the users, control system, and the third-party organizations. So it's necessary to ensure the point-to-point information security, because the malicious attack may destroy the confidentiality of the smart meter data and the integrity and availability of the remote switch control commands, and the distributed energy resources, which can be the main or the emergency backup power resource in the power grid to improve power quality and the system operation stability. But the attack may destroy the confidentiality of the user information of the distributed energy resources and the accuracy and the timelines of the power grid measurement data. The distribution automation, yeah, it's also some control equipment in the distribution side, and the malicious attack may cause the unplanned the feeder tripping, and which will result in the interruption of the power supply. For the consumer side, like the real-time electricity price, so which will help the user interface with the power system. But if this price is manipulated by the attacker, so it will have some impact in the system. The same thing as the electric vehicles. So right now, the electrical vehicles mainly play as a load in the power system, but in the future, it will play as like the generation or resources in the system. Therefore, the information to the electric vehicle and from electrical vehicle to the control center may be attacked by the cyber attackers, and which will also have impact in the power system. So here, I move to the third part of this presentation is the research framework of the cyber attack in the power system. Because as mentioned before, the the future power system is a cyber physical system. It has the power system on the left and the cyber system on the right. So to study the cyber attack, so actually we separate them into three main portions. The first one is the modeling. We need to model the cyber physical system, and we also need to model the cyber attack. Only with this model, only we know how to model them, then we know how to use this and how to quantify the impact. And the second part is the middle part. So the middle part is meaning the fused cyber and physical analysis. So in this part, based on the model, we need to do some like the risk reliability or security assessment of the power system under the cybersecurity. And also we need to study how to do the situational awareness and early warning and the detection of the cyber attack. Once we know there are cyber attack in the system, then we need to defend it. So on the top, we propose the collaborative defense framework. So that means we need to collaborate the measure the ways in the power in the physical side and in the cyber side together to deal with the cyber attack. So here is just a framework. Then I just use the cyber physical, the risk assessment, and also the collaborative control as two examples to give a little bit detailed information. So first is the cyber attack risk assessment. So here is the framework. So as we all know that the risk is defined as the product of the probability and the consequence. So the probability in this case will be the cyber attack probability. And the consequence here, we use the physical side consequence to measure the consequence of this cyber attack, because we are more interested in the physical side consequence here. So here, therefore, we have two parts. Here is a cyber attack modeling method. So this one, we were meaning to try to get to the probability of the successful target attack probability. And also here, we have the physical consequence and analysis method. Here we use a power flow and the physical side, the topology, and to get to the physical consequence. So here later I will introduce how to get these two parts. So once we have the probability and the consequence, then we can get to the risk value of the cyber attack on the power system. So for the this is for the part is for the probability calculation. So here we use the distribution network as an example. So we consider the attack in the distribution side. So here we see that the physical layer here includes the circuit breaker, section switch, and the load units. And also we have the cyber layer here. So here is the main station, and here is the slave station. So the communication between these two are the SDH communication network. And also we have the terminal layer. So this is the one interfaced with the physical layers in the distribution system. So here we use the optical network communication, and also we have the feeder remote terminal units, FRTU, to perform some measurement and calculation. So here we use this figure to give some details about the slave station, because the previous slides is the full picture. Here we move to the zoom into the slave station. And for the slave station, we can see the cyber network include three layers. The first is the substation layer. The second is the terminal layer. The third is the processing layer. And the processing layer will directly interface with the physical distribution system, the breaker, the switch, and some transformers. And from this figure, we can find that there are three potential access points for the cyber attacks. So one is the monitor host, one is the telecontrol device, and another one is the merging units, so which is for the data acquisition units. So here we change that figure into a IEC 61850 standard substation model. So in this model still have 3 layers and with different logical loads. So every functions in the server side will be a logical load in this figure. With the help of this figure, then we can build this attack graph for a slave station. So actually, this is not a full attack graph for this this figure. So we just pick the part of that, because here we concentrate on the attack on the circuit breaker. So in this one, we can find out like four intrusion areas. One is a monitor host, one is a remote interface, and the third one is a sensor, and the fourth one is a transformer. So then we calculate the probability. So first we decide the access points. Then we calculate the vulnerability, the probability calculation of the hacking vulnerability, because we use the vulnerability to try to access this logic points. So we need to calculate the probability of this vulnerability being used. So here is the methodology to the calculation. So we use some indexes from the common vulnerable scoring system. Here, these three, so the attack vector, attack complexity, and identity authentication. And also we consider the time of vulnerability exposure. So the longer the vulnerability is exposed, the less it will be used. So then the next one, so we will calculate because there are two parts from this monitoring host path. So then we need to decide which parts to use. So this based on the vulnerability probability we calculated before. And then we also need to calculate the transfer probability between the logic points. So here we use this formula, and this is based on the vulnerability factor of attack transfer path between these two nodes. So this is determined by the analytical hierarchy process. So once we have this value defined, we can form the Markov chain transition probability matrix. So here in this matrix, so every point and every parse will have its value in this matrix. So for this parse, so we use the PCHVI. So this is the calculated before. And for this parse, it will just the same thing as the probability of the vulnerability. And this is the transfer probability. So once we have this Markov chain transition probability matrix form, then we can perform like the search, attack all the parses based on the deep first algorithm. Then we can calculate for all the passes, possible passes, calculate the probability, and then some other probability to get to the probability of this target being attacked. So also, that's for the probability calculation. Then we move to the consequence calculation. So for the consequence calculation, so we calculate the instantaneous consequence and the long-term consequence. So the instantaneous consequence meaning like the total load loss and the total consumer loss. And the long-term consequence is a period one. So we consider the total load loss hours. So that's the megawatt hour and the total consumer loss hours. So we use this method, we use the analytical hierarchy process to combine the different consequence into one consequence for the calculation. So there are detailed methodology, so I will not go through them anymore due to the time limitation. So here's different situations. Then we consider different situations and the different consequence possibility to get to the formula here. Okay, so I just quickly parse this one. Okay, there are different combinations. Okay. So the second, the fourth part is the collaborative defense against the cyber attack. So based on the timeline of the cyber attack, so we actually propose a multi-time scale and a multi-line collaborative defense system. So before the cyber attack, so we use the situation. So here we call the collaborative because there are three parts. The first one is the cyber side. The bottom one is the physical side, and the middle one is the collaborative side. So for the before the cyber attack, so we can do the situation prediction and early warnings in both sides or the collaboratively. And also before the cyber attack, we can do the preventive control in both sides or collaboratively. And after the cyber attack happened, but it's not impacted the physical system yet, then we can do the emergency control in the cyber side and the preventive control in the physical side. And also we can collaborate these two controls, and we can do the identification and the tracing based on the cyber side information. So once the cyber attack has impacted the physical side, then we can do the collaborative identification, collaborative attack tracing, and the collaborative control. So this is just the framework. So here I use the collaborative cyber attack identification as an example. So here we just try to use the bilateral information to identify the cyber attack. To do that, we have a couple issues need to be solved. The first is because the physical side information is a continuous information, and the cyber side is always discrete one. So how to combine these two information together? And the second one is how to get the characteristic sequence of this cyber attack or the event sequence caused by cyber attack. And the third one is because we want to use for the practical use, so that we need to consider speed and accuracy of the methodology. So here is the way we do some information fusing. So that means we need to change the continuous data of the physical side into some discrete one. So this is a methodology used to change the continuous data to the physical, to the discrete one. So after the change, then we can put at a certain time, we can put all the physical side and the cyber side information into a set. And also for events, so it's a kind of a sequence of set. Then we can put all the events, the different times state in an events list. But we can see from this one that because the cyber physical system, the status not change frequently. So in many times, so the states are the same between two time period. Then we can simplify them to a clean one. Then we need to do the characteristic sequence extraction. So here we see the during the different testing, so we can get to the ideal states. So ideal states is that thing, every state should have happened at that time. But because of the time delay or some issues, we can see the states are not continuous, or we can see there are some extra states inside that. So how to get to the states consequence characteristic from all this data? So this is what we need to do. So here's the process we used. We just extracted the characteristic sequence under different support threshold. Here, we use a support threshold as a way to quantify the accuracy of the match. So that means we will find a set of the sequence and use this sequence to match a set of the same events samples. So we will find out what's the percentage it can find out the actual events. So in that case, we can, for sometimes we need to set up the support threshold. The higher the support threshold level, the shorter the events in that list. So that means we need to find a reasonable one to make sure that we can be used in real time. So also, as I mentioned before, we want to make our methodology accurate and also fast. So in that case, we also consider a machine learning methodology. So here we have combined the empirical sequence and the data-driven, because machine learning is a data-driven. So this is a combined model. For the empirical sequence, we normally use for the sequence with the delay. So that means due to the communication delay, the sequence is not perfect. So normally we use the empirical one. And for the ideal case, so we can use the data-driven, the machine learning methodology to get to match the events. So this is a case for the case study. So we use, because we do not have data, so we use a co-simulation platform to simulate different scenarios. All these scenarios are one of the faults, and the last one is a normal operation. Then we can do the calculation and find out the accuracy of this methodology. And also we can find compare the different, like integrated with the pure data-driven and the pure empirical methodology. So we can see the integrated model are normally the better one. Also, the time is used is quite reasonable. The last one, I will just give a quick introduce of the fast data, false data injection attack. So this example is how to use the physical side information to identify the cyber attack. So here we know that in the parse system, we have a data estimation to identify the bad data. But for the intention cyber attack, so we can use some methodology to generate the measurement to escape the bad data identification methodology. So this is the way we can generate the false data to avoid the data estimation. Then the method that we used is called the Jason-Shannon distribution. So I just moved to the next slide, because we can compare the distribution of the measurement of the data. This is a normal one. So this is the data, the difference data between two time scale, between the two times. So this is a normal one, and this is the one with the false data injection. So we can see the distribution change a lot. So based on these characteristics, so we use a Jason-Shannon distribution to find out the attack. So this is a methodology. So here we use 0.2 as the threshold. So we can see that to use the JSD. So we can find out the bad data injection. The accuracy is about 96.25%. And also we compare the JSD method with the traditional data estimation based methodology, and also other the distribution pattern based methodology, and we can find out it can provide some better results. I believe that's all for my presentations. Sorry about maybe a little bit over time, and thank you.